Alright, let's dive straight into the fascinating world of how AI can learn to think better by playing games against itself. We're looking at a framework called Spiral. So, we've seen some amazing progress recently, right? Models like OpenAI's O1 and DeepSeek R1 are showing that reinforcement learning can really boost reasoning, especially this chain of thought stuff. It's like teaching them to explain their logic step by step. But here's the catch: these methods often rely on humans doing a lot of heavy lifting. Think about it. You need experts to design tricky problems, figure out the perfect reward system, and constantly check if the model's thinking makes sense. This is great for specific tasks, but imagine trying to teach an AI everything using this method. It's like trying to build a library by asking librarians to write every single book. It just doesn't scale well when you want your AI to be broadly intelligent and tackle all sorts of new challenges. We need a way to automate the learning process itself. Enter self-play. This isn't exactly new to AI. Remember TD Gammon? It learned to play backgammon so well it beat world champions. AlphaGo used self-play to conquer Go, a game considered much harder than chess. Even OpenAI 5 used self-play to master complex team games like Dota 2. The magic is simple: the AI learns by playing against copies of itself. No human needed to tell it what a good move is; the win or loss of the game itself provides the feedback. And here's the kicker: as the AI gets better, its opponent gets better too, because it's just a previous version of the same AI. This creates a constantly increasing challenge, pushing the model to keep improving. It's like having an opponent who always learns from your mistakes. So, why haven't we seen this applied more broadly to language models and reasoning? That's the gap we're exploring here. This brings us to Spiral. The core idea is brilliant. Let's use self-play, but instead of complex strategy games, let's use simpler, two-player zero-sum language games. What are zero-sum games? Think poker or chess. One player's gain is the other's loss. Why these games? Because they force strategic thinking. You can't just guess randomly; you have to plan ahead, consider your opponent's moves, and adapt. They're simple enough that the AI can learn stable strategies and the rules are clear, so we know who won or lost. Spiral has two big advantages. First, it generates infinite training data. Every game played creates new experiences, no need for humans to label thousands of examples. Second, unlike training against a fixed opponent like a human or another static model, the difficulty constantly changes. Your opponent is always getting better, so you're always challenged. This prevents the AI from just memorizing one trick and exploiting a weak opponent. Now, implementing this vision for large language models isn't trivial. It's computationally expensive. Imagine multiple models playing games simultaneously, generating text turn by turn. That requires serious computing power and clever distributed systems. Plus, standard reinforcement learning algorithms can be unstable when dealing with multiple agents, especially when the environment keeps changing because the opponent is learning. The rewards become noisy and hard to interpret. To tackle these, the Spiral team developed two key things. First, a fully online, multi-turn, multi-agent system specifically designed for LLMs using a distributed setup. Second, and crucially, they invented something called role-conditioned advantage estimation, or RAE. This technique helps stabilize the learning process by making the rewards more meaningful, considering the inherent advantages or disadvantages of being player 0 versus player 1 in a game. Without RAE, the experiment showed the models would just stop thinking properly. So, what did they actually find? The results are pretty striking. Training a model like Qwen34B base on a simple game like Coon Poker using Spiral led to significant improvements not just in playing poker, but also on standard math and general reasoning tests. Look at the numbers: an 8.6% jump on math benchmarks and 8.4% on general reasoning. And get this, it even beat a model trained on 25, zero expert examples of gameplay. How does this happen? Analysis revealed three core reasoning patterns the model learned from games: breaking down problems systematically, calculating expected values, and analyzing different scenarios case by case. Different games seem to focus on different skills: tic-tac-toe for spatial thinking, coon poker for probability, negotiation for optimization. Training on multiple games together seems to create synergy. And importantly, this works even for already strong models. The takeaway? These games are like mental gyms, building transferable skills. And RAE is absolutely essential for this to work. Let's summarize the main contributions of this work. First, they built a powerful new framework for training LLMs using self-play across multiple games, fully online, handling the multi-agent aspect. They've even released their code. Second, they introduced RAE, a clever technique that stabilizes the training process, preventing the models from just giving up on thinking. Third, they empirically proved that this self-play approach works. It genuinely improves reasoning abilities beyond just the games themselves, transferring to academic benchmarks and even novel games. They identified the specific reasoning patterns responsible for this transfer. It's a significant step towards autonomous, self-improving AI. Where does this fit in the bigger picture? Well, reinforcement learning for reasoning has evolved. Early work focused on aligning models with human values, then shifted to directly improving reasoning using rewards based on correct answers. Spiral takes it further by removing the need for human-curated data entirely. For multi-agent learning with LLMs, previous attempts often had limitations, maybe using simpler models, simplified environments, or relying on supervised fine-tuning alongside RL. Spiral aims for full-scale, online learning. Self-play for improvement isn't new either, but earlier efforts either focused on alignment or had specific constraints, like needing human tasks or deterministic verification. Spiral shows robust transfer to challenging academic benchmarks. Finally, while games are often used to test LLMs, Spiral uniquely combines multi-agent self-play with shared parameters, fully online learning, and transfer to reasoning without any benchmark data during training. Before diving deeper into the framework, let's clarify the setup. Traditionally, we think of language models as making decisions token by token. But for games and reasoning involving multiple steps, the authors use a turn-level formulation. Think of each turn as a complete decision point. The state is the entire situation, the action is the whole response generated by the model at that turn, and the reward comes after that action. The key difference is the action is a whole sentence or paragraph, not just one word. Also, the model is expected to output its internal thought process first, denoted by think, followed by the final answer, denoted by answer. This allows us to analyze the reasoning itself. Building on the single-agent setup, we need a way to describe competitive scenarios. This is where the two-player zero-sum Markov game comes in. It's basically the same structure as the MDP, but now we have two players, each with their own set of possible actions. The crucial part is the zero-sum property. This means whatever one player gains, the other loses. Mathematically, the sum of their rewards at any given state is always zero. So, if player 0 gets a reward of +1, player 1 must get -1. This forces the players to develop strategies that are robust against each other, rather than just exploiting fixed weaknesses. It's the fundamental setup for adversarial learning. Okay, let's look at the architecture. Figure 3 gives us the blueprint. It's a classic actor-learner setup, which is great for scaling up. You have multiple actors running in parallel, each playing different games. They generate game trajectories, which are sequences of states and actions. Crucially, each actor uses the same underlying policy pi theta but is told whether it's acting as player 0 or player 1. This shared policy is key. The rewards are sparse, meaning they only get given at the end of the game based on who won or lost. All these experiences are collected and sent to a central learner. This learner processes the data, calculates the advantages using the RAE technique we'll discuss next, and then updates the shared policy pi theta. This cycle repeats, allowing the model to continuously improve against increasingly challenging versions of itself. So, how does Spiral actually use these games? It leverages three key properties. First, the games are multi-turn. Players take turns, just like in a conversation or a sequence of reasoning steps. This forces the model to keep track of the context, plan ahead, and react to the opponent's moves. Second, the zero-sum nature creates constant pressure. Since the opponent is always evolving, the model can't just find a single winning strategy and stick to it. It needs to be adaptable and develop robust tactics. Third, and this is the clever part, both players share the same neural network, the policy pi theta. How does this work? Through role conditioning. Before the model generates a move, it's given a prompt specifying if it's player 0 or player 1. This allows the single model to learn different strategies for different roles. As the model gets better at playing player 0, it's also getting better at playing player 1, thus creating a natural, self-adjusting curriculum. What's the goal here? In theory, you could train two separate models, one for player 0 and one for player 1, each trying to maximize its own score. The equations show this objective function j for each player. However, Spiral uses a single shared model, theta. The role conditioning allows this single model to learn different strategies depending on whether it's player 0 or player 1. To optimize this shared policy, they use a standard reinforcement learning technique called reinforce. The gradient tells us how to adjust the model parameters theta to improve performance. The equation looks a bit complex, but it essentially sums up the log probability of the chosen action multiplied by the total reward r for the trajectory, separately for player 0 and player 1. The problem is that using the raw total reward r can be very noisy, especially since the opponent is changing constantly. This leads to high variance, making training unstable. This is where role-conditioned advantage estimation, or RAE, comes to the rescue. Remember the high variance issue with the raw rewards? RAE tackles this by introducing separate baselines, b sub g, p, for each game g and each player role p. Think of a baseline as a moving average of the expected reward for that specific role in that game. It's updated using an exponential moving average, giving more weight to recent rewards. The advantage a sub g, p of tau is then calculated simply as the actual reward r sub p of tau minus this baseline b sub g, p. By using the advantage instead of the raw reward, the updates become much less sensitive to the overall scale of the rewards and the non-stationary nature of the opponent. The final gradient update uses these advantages. This stabilization is critical. Without it, the models tend to stop thinking properly, a phenomenon they call thinking collapse. Algorithm 1 lays out the whole process. It starts by initializing the baselines for each game and role. Then it enters a loop. In each iteration, parallel actors collect game experiences. They pick a game, play it out, and record the trajectory and the final rewards. These experiences are collected into a batch. Next, the learner processes this batch. For each trajectory, it updates the baselines for both players using the EMA formula and calculates the advantages. Finally, it uses these advantages to update the shared policy parameters theta. This cycle repeats until the model converges. It's a clean, iterative process of playing, learning, and improving. How did they actually build this thing? They used existing frameworks like OAT, which provides tools for distributed actor-learner setups. The actors, the ones playing the games, used efficient libraries like VLLM for fast inference and Text Arena to simulate the game environments. The learner component implemented the policy gradient algorithm with the crucial RAE component. The whole system is designed to handle the full complexity of multi-turn, multi-agent reinforcement learning for large language models, enabling truly online training where the model adapts continuously. Alright, let's see what they actually tested. They had 4 main questions. First, the big one. Does playing these games actually make the model better at reasoning, especially in math and general knowledge, without any special training data related to those topics? They wanted to see if the game itself teaches transferable skills. Second, is the self-play approach better than just training against a fixed opponent, like a human model or a random player? Does the adaptive difficulty of self-play lead to more robust learning? Third, do different games teach different things? Like, does tic-tac-toe improve spatial skills while poker improves probabilistic thinking? And if so, does training on multiple games combine these skills better? Fourth, and critically, is that RAE technique we talked about really necessary? Does it prevent the models from just giving up on thinking during training? To test these ideas, they picked 3 specific games. Tic-tac-toe is a classic for spatial reasoning. You need to recognize patterns, block your opponent, and plan ahead. They hypothesized this would translate to geometry and spatial problems. Then there's coon poker, a simplified version of poker. It involves hidden cards and betting, requiring you to calculate probabilities, guess what your opponent might have, and make decisions under uncertainty. This should help with probability and expected value concepts. Lastly, simple negotiation is a game where 2 players trade resources like wood and gold, but they value them differently. Success here needs planning, understanding what the other person wants, and communicating strategically. This should improve skills in optimization and balancing multiple goals. Each game targets a different type of cognitive skill. They used Quen 3-4B base as the starting point. Training ran for 400 steps, collecting a lot of game data. They used standard optimization settings. Now, how did they measure success? They looked at several things. First, how well did the trained model play against a strong baseline model Gemini? Second, could it generalize to new, unseen games that required similar skills? For example, could a tic-tac-toe specialist handle Snake? Third, and most importantly, did it perform better on standard math and reasoning benchmarks like Math 500, Olympiad Bench, GPQA, etc.? All evaluations were done in zero-shot mode, meaning no examples from the benchmark were given during training. Finally, they analyzed the actual reasoning traces generated by the model in both games and math problems to see which specific reasoning patterns emerged and transferred. Let's look at the results for the first big question: does self-play improve reasoning? Table 1 shows the scores on various benchmarks. The key takeaway is the row labeled Spiral Coon Poker. This model was trained only on Coon Poker using self-play. Look at the scores. Significant improvements across the board, especially on Minerva Math, an 18.1% jump. And remember, this model never saw a single math problem during training. It learned these reasoning skills purely from playing poker. It even outperformed a model trained on 25, zero expert examples of gameplay. This is pretty compelling evidence that the competitive environment itself is teaching valuable transferable skills. So how exactly does playing poker improve math skills? The researchers dug deep into the reasoning traces the models generated. They used GPT 4.1 as a judge to classify these traces into recurring patterns. They identified 3 main ones. First, case-by-case analysis, breaking down a problem into distinct scenarios and examining each one systematically. Second, expected value calculation, figuring out the average outcome of different choices, considering probabilities. Third, pattern recognition, spotting recurring structures or regularities that can simplify the problem. The cool part is that these patterns showed up in both the game traces and the math solutions. It suggests the gameplay is forcing the model to develop these fundamental reasoning techniques. Figure 4 visualizes this. The left panel shows how these 3 reasoning patterns grew stronger within the game itself as training progressed. The middle panel shows how effectively these patterns transferred to math problems. Notice case-by-case analysis transfers almost perfectly. 72% in games becomes 71% in math. This suggests it's a very general skill for structuring thought. Expected value calculation transfers moderately, maybe because it's more specific to probability problems. Interestingly, pattern recognition actually shows amplification. 35% in games jumps to 45% in math. This might be because math inherently involves pattern recognition and gameplay just boosts this existing skill. The right panel confirms the link. As these patterns develop, the model's scores on math benchmarks go up. It's clear evidence of transfer. So, why does this transfer work? The authors propose 3 reasons. First, the competitive pressure of self-play is intense. Since the opponent is always getting better, the model can't just memorize answers or exploit simple tricks. It has to develop genuine reasoning. Second, the games themselves are relatively pure. They strip away the complexities of real-world domains, focusing on core cognitive operations like breaking down problems, evaluating options, and synthesizing information. These basic skills are likely to be useful everywhere. Third, the way the model learns to output its reasoning during gameplay, the think/answer format provides a template or scaffold that it can reuse when tackling math problems. So, the first major finding is clear. Playing these games builds transferable reasoning skills, and it happens through the development of these three core patterns. Now for the second question, is self-play really better than training against a fixed opponent? Figure 5 compares different training scenarios. Look at the random opponent line. It completely fails. Why? Because the random player always makes valid moves, the model has to generate perfectly valid actions every single turn to get any reward. Over long games, this is incredibly difficult to learn. It's like trying to walk a tightrope blindfolded. Now look at the Mistral or Gemini opponent lines. The model learns, but eventually it finds a way to beat the fixed opponent. But once it does, it stops learning. It's overfitting to the opponent's predictable strategies. It doesn't generalize well to other tasks. Self-play, however, maintains a consistent challenge. The opponent evolves, keeping the model engaged, and the results show it leads to better performance on both game-playing and the reasoning benchmarks. Table 3 shows the win rates against the evolving self-opponent stay around 50%, while against a fixed Gemini opponent it starts at 0 and only catches up later. The second finding is clear: self-play's adaptive difficulty is superior. Third question: do different games teach different things? Table 4 shows specialists trained only on one game. The tic-tac-toe specialist is great at tic-tac-toe and also does well on Snake, another spatial game. The poker specialist is dominant in poker and surprisingly good at pig dice, a probability game. The negotiation specialist excels in negotiation and truth and deception, a communication game. This confirms the games are indeed developing specialized skills. But what happens when you train on multiple games? Table 5 shows the multi-game model. It's competitive on all the original games and significantly better at the new ones, especially Liar's Dice, which combines bluffing and probability. Table 6 shows even a strong model like DeepSeek Roan gets a boost from multi-game training. The third finding is that combining these specialized skills leads to synergy, creating a more versatile and capable reasoner. Finally, the fourth question: is that RAE technique really necessary? Figure 6 shows the dramatic difference. The orange line uses RAE, the gray line doesn't. Look at the top row. With RAE, performance stays stable across games, math, and general reasoning. Without RAE, the math performance crashes after about 150 steps, and general reasoning drops too. Now look at the bottom row. The response length, a proxy for thinking, plummets with vanilla reinforce, indicating the model stops generating detailed thoughts. The policy gradient norm also becomes unstable and collapses. This is the thinking collapse phenomenon. The fourth finding is undeniable. RAE is absolutely essential for stable training in this multi-agent, self-play setting. It prevents the models from degenerating into simple, unthinking responses. So, wrapping it all up, Spiral offers a compelling new way to train language models to reason better, using self-play in simple games and eliminating the need for massive amounts of human-curated data. Technically, they provided the tools, a scalable multi-agent system, and the crucial RAE technique. Empirically, they proved it works: significant reasoning gains, even surpassing traditional methods, broad transfer of skills, synergy between different games, and benefits for models of all strengths. It's a promising step towards more autonomous AI development. Of course, there are limitations. While it removes the need for human problem sets, it still needs carefully designed game environments. The games used were relatively simple. Scaling this to more complex scenarios is a challenge. It's also computationally intensive. And the performance eventually plateaus. The evaluation focused on academic benchmarks, not necessarily real-world common sense or ethical reasoning. Looking ahead, the possibilities are exciting. Could this be extended to cooperative games? Games with hidden information? Could we design games specifically to target known reasoning weaknesses? Understanding the precise link between game mechanics and skill development could lead to even more principled training environments. The vision is of AI agents that continuously challenge each other, pushing the boundaries of reasoning further and further. Ultimately, Spiral suggests a fascinating possibility that complex reasoning skills can emerge from relatively simple competitive environments without needing explicit instruction on every topic. It highlights the power of self-directed learning and the potential for AI to develop its own curriculum through challenge. This might shift our perspective on how intelligence emerges, perhaps pointing towards systems that learn and evolve autonomously through interaction, rather than just following detailed human scripts. It's a glimpse into a future where AI agents continuously push themselves to think better, all through the simple act of playing games.